Now we are going to discuss polynomial functions that have a degree higher than 2. And I started the notes here with the definition of a polynomial, but we did look at this in the last section as well. So we just put it here to remind ourselves that polynomial functions, so this is a function of x. Of course, we could use different variables, but polynomial functions in x have powers on the variables, and those powers have to be whole numbers. So non-negative integers in my definition here, those are whole numbers, 0, 1, 2, 3, etc. And then the coefficients are just real numbers here. They can be any types of numbers for the coefficients. The highest power is referred to as the degree of the polynomial, right? That's all review. And then if this is, I mentioned this last time, if these powers are in descending order, the powers on the variable, then the polynomial is in standard form. So if it's in standard form, the highest power is first, and then we refer to this as the leading term. And of course, a sub n would be the leading coefficient. And if it's in standard form, if there is a constant term, there may not be a constant term, but if there is, it will be the last term in the list, and that's the degree 0 term. Okay, so just a quick example. Determine if these 5 functions here are polynomial functions. And so all we need to look at are the exponents on x. These are all functions of x. This one is, yes, the degree, of course, would be 4, and then I'll just abbreviate LC for leading coefficient, would be 3. So watch and make sure that it's in standard form before you just look at the first term. You want to make sure that is the true highest power. B is not a polynomial because of the -1 on x. Don't refer to this as the degree if it's not a polynomial. It's just an exponent. C is a polynomial. These are the coefficient, well, -2 is the coefficient of the cube term. And these 2 and 3 are whole numbers, so yes, this is a polynomial. The degree is actually 3. That's higher than 2. And so the leading coefficient is the coefficient in front of the x cubed term, including the sign there. It's negative, whoops, not -2, but negative square root of 2. D is actually not a polynomial because the square root of x is x to the 1/2, right? And so that's not a whole number on the variable. Now you might be saying, well, why was this okay over here with this square root? Well, that's because it's not on the variable. This 5 to the 1/2 power is just the coefficient. It's not the exponent on the variable. The exponent on the coefficient can be anything. And then E, we have powers of 5, 3, and 2. So this is a polynomial. 5 is the highest power, so it's degree 5. And then the leading coefficient is actually the fraction 1/5. Since we're dividing by 5, we could pull that out, and the coefficient is 1/5. Okay. These notes here, I actually had these first 3 in the last section, so I just stated them here again for completion. I think the one thing I didn't include was that I didn't talk about what p at x equals 0. That's a constant function, but we say it doesn't have a degree because 0 could be x to, the first. It could be, 0 times x to the first. It's not equal to x to the first, of course. 0 times x to the first, it could be 0 times x squared. So it's not clear what the power is, and so we say it has no degree. As long as it's not 0, our constant, then we say it has degree 0. So like p at x equals 5 would have degree 0. Okay, and we talked about how linear functions, when we have a non-zero slope, we have a polynomial function of degree 1. Quadratics are degree 2, and of course they're parabolas. And then today we're mostly going to talk about degree 3 and higher. So we have special names for degree 3 and degree 4. Degree 3 is sometimes referred to as a cubic function, degree 4 as a quartic, and then once we get higher than that, we usually just say degree 5, degree 6, etc. And we don't always use this, so we sometimes just say degree 3 or degree 4, of course. But if you see those words, I want you to know what they mean. All right, and then the next page, these are just some examples of some graphs. So here's a degree 0, right? Here's a degree 1, degree 2. Of course, these just keep going up by 1 degree. And the higher the degree, of course, you can have more terms, right? Like this degree 4 does have a power of 3, 2. There's no power of 1, and then there's a power of 0. The more terms you have, especially if there's a lot of sign changes between those terms, that's where you're going to get more turning around in the function. Like this one here, the y equals x cubed minus 3x plus 1, we we've graphed y equals x cubed, right? It looked kind of like this. And so notice these extra terms are what creates the pulling and changing of the function values. You know, as x gets bigger here, you know, like here you have x equals 1, here you have x equals 2, x equals 3. If you don't have the negative 3x here, you're never going to get the negative value. Things are just positive and going to get positive, right, with the x cubed. It's this negative 3x term that will actually pull it down and make it negative for a little bit. We're going to talk more about that idea. But, you know, keep in mind that one thing you can say about polynomials is the more terms you have with varying signs, it's not necessarily going to have a lot of turning points, but you know, that's what creates the turning. When I say turning points, I mean the point where this, you know, changed from decreasing, now all of a sudden it's increasing. Here it was increasing, now it's decreasing. So this graph has 3 turning points. This degree 5, there are no other terms. So as x gets bigger, x to the 5th is just going to get bigger and bigger and bigger. This has no turning points. As you read this from left to right, excuse me, x is getting bigger, y is just getting bigger. This one has 2 turning points. This one just has 1, of course, and quadratics will always have 1 turning point because they're parabolas. And this one, of course, has no turning points. Okay, and neither does this one, of course. The other thing I want you to notice about these graphs is that the domain of all of these is all real numbers. And with a polynomial, that's always going to be the case because we just have powers of x. And there's no problem with raising a real number to any power and then multiplying it by a number, adding and subtracting. So the domain is always all real numbers. Another thing we know about all polynomials is that they're always continuous, and that has to also do with the domain. But you know, there's no, for example, there's not going to be a hole where you jump. Everything is defined. But not only that, we can have, here, let me show you a picture. Like, for example, a piecewise function that looks like this has a domain of all reals, but this is not continuous because of the jump from here to here, right? So this is not continuous. With a polynomial, you're never going to have any jumps or breaks in the graph. I actually have this written up on the next section, on the next page. So notice how everything's connected for all of these. So these are always continuous. and there's no holes in the. The other thing we know about polynomials is that they'll never have like a pointy V shape on them. If they turn, it's going to be a smooth curve through that turn. So all of these are nice and smooth through their turning points. They have no corners like the absolute value function has a corner. That's the point, right? Or the sharp point, I should say. So I have these properties up for you right here. So I already talked about the domain. The function is continuous. In other words, there's no breaks or jumps or holes in the graph. So the break, by the break I mean the hole. And then the graph is a smooth curve, like I said. There's no sharp corners like the V shape, you know, there's none of that. A cusp is kind of like an inverted V where you have a curve on each side of the point, but there's no, you know, basically no sharp edges. Everything's smooth. Other, you know, the lines don't have curves, of course, but they don't turn, so that's okay. These two, I talked a little bit about the turning points, but I actually didn't give as much information as we actually know. First, for number 4, the x-intercepts, I didn't talk about that at all, but there's at most n. N is the degree, right? Degree n. So a good example of that would be the quadratic, which is degree 2. We talked about in the last section how we could have one x-intercept if the vertex is on the x-axis, 2, like this one does, if you know we cross the x-axis twice, or there could be 0 if the parabola is shifted up and doesn't, you know, cross the x-axis at all. Here's another good example. If you shift this up, you can see where you could have 1, or you might just have 2 if the x-axis lines up right here at these 2 points. And of course this one does have 3, and that's the most it could have. So the most it could have is also related to the maximum number of turning points, and that's at most n minus 1. And so we talked about these turning points here. This one is degree 4, and it has 3. That's the max it could have. This degree 5 one has none. So you don't have to exactly have one less than the degree for the turning points. This has no turning points, and it's a degree 5. We don't have to have 4 turning points. Again, the turning points are going to be created if you start bringing in some extra terms. So let's just use the graphing calculator to show you what I mean. Let's see here. So those y equals x to the 5th, you know, we already know what this graph looks like, but I'm just going to put it on here. And let me check my window. That looks fine. Okay, so if I add another term, I'm going to make it negative. If I make it positive, this side is going to pull the same way. So say it's three x. Let's do, let's make it an even power, 4. Okay, so here's what I was talking about. Zoom, or let's not zoom, let's do this. Window, negative, let's try 15. I'm not sure how high that thing goes. Okay, it goes higher than it shows, but that's okay. So what I was saying is on this side, when x is positive, now I graphed y. What did I graph? I forgot. X to the 5th plus 3x to the 4th. When x is positive, these two things are working together, and that's why you're not getting another turning point on this side. But when x is negative, x to the 5th is a negative number, so this term is creating a negative number, but now this x to the 4th here becomes positive. And that's what created another turning point, because these two things are working against each other in a sense. And so that created a turning point. If I make this a degree 3 instead, we're going to lose that turning point because now these are both negative at the same time, so they're working together and just pulling this thing down, if that makes sense. I hope you can, I have a glare there, I hope you could see that. Here, let me show you both of these again. So here they're working together, or they're working against each other. This was with the cubed. Y equals x, or plus 3x cubed. So if I change it to the 4, that's what created the extra turning point on this side. Okay, and you could play around with different terms, different signs, different powers, and see different, you know, how that affects the x to the 5th. Let's talk about the power functions now, and then maybe we'll play around with this a little bit more. Once you know what the basic power functions all look like, this makes it easier to recognize what each graph is going to look like. So the power functions are polynomial functions that just have one term. They're monomials, and you know, of course, you've got ax to the n, so whatever this degree is, degree n. You're not going to have a bunch of turning points with these. These are just your basic, you know, degree 1, degree 2, degree 3 functions. We've already talked about degree 1, degree 2, and even degree 3. We've graphed y equals x cubed. So we'll look at, and then now we actually have on this page y equals x to the 5th. We're going to look at the relationships between those. I want to consider first even. The evens are all alike, and then the odds, okay? So the evens, degree 2, of course, y equals x squared, we know what that looks like. Here's y equals x squared. So I'll graph it quickly since we're pretty familiar with this already. And then next would be y equals, I'm just going to use a equals 1 just to make it easy, okay? So we've got y equals x squared, now y equals x to the 4th. So what will happen with y equals x to the 4th, and here's where I should have brought some different colors, of course I forgot. So 0, 0 is going to be the same. And then when you plug in 1, 1 to the 4th is 1, negative 1 to the 4th is 1. They almost look like they're the same. But what I want you to, here I'll do this, x and then x squared. That's going to be the point on x squared, and then x to the 4th. Okay, so we've got 0, 0, 0, 1, 1, 1, negative 1, 1, 1. Those are the three we have so far. But what I want you to think about is a point between 0 and 1, like 1/2, and I'm just going to use 0.5. So when you square 0.5, of course you get 0.25, that's that point right there. When you raise it to the 4th, you get 0.0625. What I want you to notice is that for this input, this is actually, x to the 4th is actually smaller than 0.25 because of the small value. So this is going to be down here for x to the 4th. But once you get past 1, like when you put 2 in, of course 2 squared is 4, that's these points, but 2 to the 4th is 16. So for this function, 16 is way off the graph. So what you get is more of a U shape. It looks very similar to it's not a parabola now, okay, but it looks like a parabola. And see how the power of 4 is a lot bigger than the power of 2, and so this thing shoots up a lot quicker. But between -1 and 1, those numbers are actually smaller. Now, if we do this for the next even power, x to the 6th, these are going to be the same. But then the 0.5 to the 6th, 0.015625. that's a really small number. So the next even power function will be even more of a horseshoe shape. These points will be even lower, and then 2 to the 6 is really big, 64. So these things grow really, really fast. The higher the power, the more U-shape you're going to get. So let me see here. I don't have any pens on this desk. I'll just have to use this. But you're going to get an even, so 2, you plug in 2 or -2. I didn't put in -2, but of course these are even functions. They have symmetry. So on either side here, you get even more of this like horseshoe. It almost looks like they're vertical lines. Whoops, I put that in the wrong spot a little bit there. But they're not vertical, of course, because these are functions. But you just get this, u. So the, y equals x squared is like that, and then x to the 4th comes below it a little bit. It's so hard to draw this. Maybe I'll just try it on the calculator and see if that helps. X squared, x to the 4th, x to the 6th. And then let's change the window to -4, and then the range is 0 to infinity, so I don't need to go too low here. Let's just do -5, and then let's make this 30. Okay. So it's hard to see right here. We'll zoom in a little bit around here. But see, here's y equals x squared. Here's y equals x to the 4th. Here's y equals x to the 6th. And this is just going to get to be a more and more of a tighter u the higher we let that power go. X to the 8th, x to the 10th, etc. Get rid of x to the 8th here. So those even power functions behave very similarly. Here, let's zoom. Let's do a box around here a little bit. Okay. Want to be less than -1 and then greater than 1 when we do this. There you can kind of see how they intersect each other, and the higher power ones actually go below the lower power ones. Okay, and like I said, these are even functions. They have symmetry through the y-axis. Whoops. Make sure I'm writing on screen here. Even functions. And the even power changes the sign of the input to positive on both sides, right? When you plug it in the plus or the minus, you get the same output. Everything becomes positive. All right, well, let's look at the odd degree ones now. Of course, we know the first one, y equals x, would just be our line with a slope of 1. And then we have also graphed y equals x cubed. We did that back in chapter 2. So there's y equals x cubed. Okay, so we plug in an x, and then that's going to be the output for y equals x, so I'm not going to write it x. Okay, then x cubed, and then we'll look at x to the 5th, and then x to the 7th. So of course, the 0 is going to be the same for all of these functions. They're all going to go through 0, 0. The 1 is going to be the same, right? When you raise 1 to any power, you get 1. So all of the functions will go through here. Likewise, the -1, because these are odd, you're going to get -1 for all of them. So this point is shared by all. But when you take values that aren't one of these three, you're going to get something different happening. So when we put the 2 in to the x cubed, or the -2, of course we got 8 or -8. Because of the odd power, the sign stays the same. When we raise 2 to the 5th, that's 32. I don't need a calculator for that. And then -32. So this is way up here off the graph. And this is, of course, way down off the graph. And then in between 1 and -1, something similar is going to happen like with the even powers. So when we put in a half, or 0.5, or -0.5, so 1/2 cubed is 1/8, but not in fraction form. Am I thinking? Why can't I remember what 1/8 is? It's 1.125. I'm sorry, I should know that. I had a mental block for a second. -0.125. So here, whoops, I put that in the wrong. Oh no, that's where I wanted it. I'm sorry. So here you have 1/2, 1/2 for y equals x, and then for y equals x cubed, you've got 1/2 and then 0.125. I probably don't have my turn strong enough there. And -1/2, -0.125. And when you plug that into x to the 5th, so it's 0.5 to the 5th, it's 0.03125, and of course this would be the opposite. That's really tiny, okay? So what happens with the y equals x to the 5th is you get, of course the 2 is way down here at -32, it's off of the graph. You get, and you don't want to make this look like it is vertical, but it kind of almost does. You get a more flattened out shape here, and then once you get past 1, the thing just takes off. Okay? So what I want you to notice is because of the odd power, this comes down here, but other than that, it's basically similar to the even powers. These go opposites. We call this the end behavior. The end behavior of this function, or all of these functions, is that as x becomes infinite in a positive direction, we sometimes use this notation, arrow, to mean x tends to infinity, then we'll use y because we have a bunch of different functions here. Let's just use y in general. Y is also becoming infinite. You can see that on the graph. In all of these, the bigger x is, the bigger y is. But on this side, as x goes to -infinity, so this means instead of reading the graph from left to right like we usually do, we're thinking about going this way. What's happening as x goes away from 0 to the left, the y values also are tending to -infinity. All right, and so I didn't do x to the 7th, but you can, if you understand the pattern, what's going to happen is this just becomes stretched even further and really flat in here. It almost looks like it would become vertical with the x-axis, but it won't. And then, of course, it goes through 1, 1, and then just takes off super fast. So the higher the power, the more exaggerated that turn through 0, 0 is. It's not a turning point, however, because everything is always increasing. This function is always increasing. Back to this one, I should write the end behavior in. So the left or the right end behavior is the same as with the odd functions. As x goes to infinity, y goes to infinity. But the end behavior to the left is opposite. As x goes to -infinity, y is actually also going to infinity, because even power makes everything positive. Okay? All right, once we know what those basic power functions look like, we could graph different versions of them using transformations. Like if we know x to the 4th is the u shape, and remember they're going to go through -1, 1, and 1, 1. Just use that. Then negative 2x to the fourth would just be a reflection of that. Here, let me put the U shape in here. Now, this is not a parabola. It flattens out a lot more than a parabola. And keep in mind, this does ever so slowly keep, spreading apart. It does not, we don't get vertical lines here. So the negative 2 would just, we take this 1 and then times 2 is 2, but you reflect it. So negative 2, and then, when you put 2 in originally, you would get 16. So now you're going to get negative 32. It's just going to pull everything even faster. It really does look like that you would get vertical lines, but you don't. Okay, so this is slightly stretched. It's just so small it's hard to see. But it has the same effect as their transformations always do. And then y equals x to the fifth here would be our basic function. So this x to the fifth has a pretty good tight curve in here. Something like that is a rough sketch. Right? And then this would just mean shift left to left 4 units, excuse me. So looks something like that. Doesn't have to be perfect. Just want you to understand that curve in there and how it gets tighter the higher the power is. Okay? So there's the graph we're looking for. All right. So now let's talk more about end behavior, because we don't always have just one term, of course. Here we have x to the fourth, and now we look at all the other terms. These are going to create the turning points and what's going to happen here. And so I'm going to make a chart similar to what I did when I graphed the power functions. So if we just have x to the fourth, and then actually I'll just make one for each term so we can see how they're interacting. Okay, so this is a -1 here. So for a given value of x, we'll start with 0 and work our way out again. Now y is just going to be the sum of all of these. So you add up all of these terms to get y, right? So of course these are all 0 when we have 0, but when we have a -1 for y because of the constant term. All right, let's go to the right first. So in other words, in our graph, we're going to think about as x is going to infinity, what's happening. So if we do 1, 2, and maybe we'll do 3. Okay, so 1 to the fourth is 1. Of course, these all just become 1, so we get the coefficients, -4, 9, -1. So basically you've got, numbers here, and the ones that add up to more than the negatives, so that the result will be positive. This is 10 minus 5, which is 5. 2 to the fourth is 16. 2 cubed is 8. 8 times -4 is -32. 9 times 2 is 18. And then we have a -1. So look at this one is the strongest this time in comparison to the others, but these still add up to more than the negatives. So we've got 16 plus 8 is 34, minus 33 is 1. 3 to the fourth is 81. Let's see, 3 cubed, 27 times 4 is... Wait, did I do the right? Yeah, 27 times 4 is 108, so -108. 9 times 3 is 27. -1. So see, this here is going to win out this time. No, wait, what's it? I should maybe speak too soon. 81 plus 27. Oh, 108. These add up to 108, so this balances this out, and we're back to -1. So notice it was negative, it was positive, positive, now it's negative again. 4 to the 4th is 256, yes, 256. And this is basically 4 to the 4th as well, because 4 cubed and then times 4. So this would be negative 256. 9 times 4 is 36. And then we still have the negative 1. This one always has the same effect because it's constant. These balance each other out now, and then 6 minus 1 is 35. Okay, 5 to the 4th, 625. I need to do a couple more before you see what's going to happen here. 5 cubed is 125, so 4 times 125. So negative 500. This is 45 minus 1. Okay, so 625 minus 500 plus 44, 169. Okay, I'm going to do one more and then I'll explain why I'm doing this. Okay, 6 to the 4th, 1296, negative 4 times 6 cubed, negative 864. 9 times 6 is 54, and then that's still always negative 1. Okay, so why am I doing all of these numbers? Well, what I want you to notice is the powers tell us how strong these terms are, basically. This one always is the same strength. It's pretty weak. It only brings down minus 1 each time. This one is a little stronger. We just get a multiple of 9. These two are really strong. The high powers of 4 and 3 have a bigger effect than just a power of 1 or a power of 0. Notice, in fact, that, and these have opposite signs, right? So let's just compare these two columns. At first, this one is stronger. When we plugged in 1, this one wins out of these two. Like say it's a war. Which sign is going to win out? This one wins, this one wins, this one wins. They're equal. And once we get past that point where they're equal, this higher power is now going to win every time. In fact, this one is going to grow so much more rapidly than this one. This one's never going to take over again. And so the point of this is that no matter what pull these other terms have here, they will have an effect kind of in the middle of the graph around the y-axis, in the center. But once you get out towards larger and larger x's, either to the right or to the left, this high power, your leading term, is the only thing you really need to look at to determine the end behavior. This will be the strongest once x is big enough. If x is small, then some of these might actually be stronger at some point. But this one will always win in the end. Okay, and I did this for the positive numbers. We could go through and make a similar argument for the negative numbers. I'd probably do a different example though, because if this is a negative, here's what, you can always figure out the sign just by looking at the sign of the coefficient and the power. If x is negative, this is positive, and if x is negative, this is actually positive. These two things will actually work together when x is negative over here. So if you wanted to look at two that work against each other, actually these two work against each other, because if x is negative, this will be negative, but this is positive. Okay, so you can kind of see what terms are stronger as x gets bigger and bigger and bigger, and what their signs are. And that pull of opposite signs is what creates your turning points. So I'll plug this. We know what x to the 4th looks like already. Let me clear these out. And let me put my window back to my normal window. Make sure that I don't get that glare. Wait. If I turn this there, that helps. Okay. So y equals, so here's our x to the 4th, and we already know that the end behavior for this is as x gets big, y gets big, as x goes to negative infinity, or so in both directions getting far from 0, y gets big in both cases. All right, but if we look at y equals x to the 4th minus 4x cubed plus 9x minus 1, see how you get the turning points? But the end behavior is the same as y equals x to the 4th. So near 0, you get the pull back and forth, but to the ends, you've got this, basically the same behavior as the highest power. So what this brings us to is what we call the leading coefficient test, or the leading term test. I usually refer to it as a leading term test because we need to look at more than just the coefficient. We need to look at the exponent as well. So of course it's only the leading term if the polynomial is in standard form. You want to make sure you're looking at the highest power. So ignoring all these other things, we know that the behavior to the left and to the right just by looking at the degree and the sign of a sub n. So if this is a positive leading term or leading coefficient and n is odd, you might have whatever going on in here, but we know that the behavior to the right and to the left are going to be opposites as x gets bigger. P at x, I'll use P at x this time since that's what I used in the notation here. P at x also gets bigger and bigger and bigger. X is positive and this doesn't change its sign, so everything's positive. Here, as x is negative and n is odd, so that's going to still be negative and the coefficient's not going to change the sign. All right, so this notation, the arrow to infinity is just saying tends to infinity. Here, in other words, gets bigger and bigger and bigger. These get smaller and smaller and smaller. In a sense, it's still large, though. It's large in the negative direction, right? It's still far from 0. When they're even, the end behavior is the same, is like a mirror image on both sides, like this. Again, the extra terms here can create something going on in here, whatever it is. We know, we can talk about how many turning points it could have and how many intercepts and that it's smooth and all of that. But just in terms of the end behavior, that's what we're interested in here. As x goes to infinity, p at x also goes to infinity. And here, as x goes to negative infinity, p at x goes to positive infinity. Put a little plus there to make sure that's clear. And then the only thing that changes if we have a negative coefficient is you get a reflection, basically, so these will just go opposite. So you're going to get this heading downward to the right and upward to the left. Again, there might be something like this. Make up whatever you want in the middle. Okay, so as x goes to infinity, p at x will actually go to negative infinity because of the reflection. And on this side, as x goes to negative infinity, p at x will now go to infinity. And then in the even case, these will both head down. Something like this. So as x goes to infinity, p at x goes to negative infinity. And here, as x goes to negative infinity, p at x also goes to negative infinity. So of course, polynomials are a lot more complicated than quadratics. We can't just look at it and know exactly how many turning points there are going to be. Like with a quadratic, we know it's always a parabola, right? And there's always one turning point. Of course, when I say polynomials, I mean polynomials degree higher than 2. But what we do know for sure is the end behavior. We can just look at this first term, and if we know our power functions, basically the end behavior will be just like the power function, the 1 degree function. that has the same degree. Or did I say one? I said the one term function that has the same degree, excuse me. All right. I don't know why that changed font right there. That's weird. Anyway, I think I'm going to take a break here before I do this. This part, zeros, we've actually been doing this already, so this is review. You could try these maybe on your own before you start the next video and see how you do. And then we'll talk more about that relationship between the degree and the number of intercepts, etc. And we'll sketch a few graphs. We don't do too many graphs of polynomials by hand because they are complicated, and of course we have technology now that we could get a graph easily if we needed to. But it's good to do a couple by hand just to make sure you really understand what's happening with the terms. Okay, well, let's take a break.